So first let's consider like z is contained in L. The valuation is z minus 1 is bigger than 0. Let's consider this function fz of x. And xn z minus 1 to the power n. Certainly this is a continuous function, and also this converges because this vp z minus 1 to the power n is close to infinity. So that means this is goes to 0. And in p-adic analysis, you just need the general term to be 0 to be converged. And you can see, observe that f zk for k contained in n is nothing but z to the power k. This is just Newton's binomial theorem. You just expand it, right? This is just z power k. So we just write this instead of fzx, we just write on this as z to the power x. Because x k in here, you get z to the x. So you can check zx plus y is zx and zy. You need to use binomial identities to prove it. Now let's give an example. This is an easy example for you to do p-adic analysis. This is z 1/2. So this is n equals 0 to infinity xn. So it's 1/2 z minus 1 to the n. So this is 1/2. So a little exercise is this. Take z is 16/9. You can check. Now you find z 1/2. If you using this power series in Q in R and Q7. So exercise. So it's a small exercise for students who want to do p-adic analysis. It's a very easy one. Now what we need is let zeta is zeta to the pn. So it's pnth root of unity, primitive one. Then we know this vp zeta minus 1 is 1 over p minus 1, p to the n minus 1. This is bigger than 0. So we get that we can take z equals zeta. So we have zeta x plus p n is zeta x. Certainly, this is always true. So zeta x is locally constant. So this is a locally constant function. And we also have, moreover, we have this 1I plus p to the n dp x. So this is a notation. So if we 1x is just a characteristic function of x. So it just means it's 1 if x, 0 if otherwise. This is a notation, characteristic function. So you can find that this is nothing, but you can check. It's 1 over p to the n. So the summation is over all this kind of data. So it's z minus I z to the x. Okay. this is easy to check. It's basically it's just a summation. You just take a circle. All this nth root of unity. The sum of all this is 0, right? Primitive 1, and then you can check this. Okay, so now we can have one proposition. The first position we want to have. So we let this L. So this is a locally constant function. So it's generated by this z to the minus x, right? But we don't need this yet. But we first need this instance in C0, CPL. So certainly this is not complete, but this is dense here. And this proof is easy. It's also analysis. You just say Fk. For example, Fk is just I is 0 to pk minus 1. Fi 1I plus p to the k, Zp. So this is a locally constant function, but you can find this goes to f for any f contained here. So that means this is dense. To prove this, why this is true, you need to use, because Zp is compact. So continuous function in a compact set is uniformly continuous. So this is a mathematical analysis. I think some of you still remember it, right? If it is continuous in a closed compact subset, in R, that's in R at that time, then it's uniformly continuous. Okay. So, but the proof is just like this. Now we can prove, using this fact and this, we can prove, recall we can prove that B equals C0. Well, B equals 6. See, we evaluate, so suddenly B is containing here, and it's closed. By the definition, it's closed. So what do we need to do? If we know this, so if we have this, then we are done. Because this is dense inside here. Okay? So we just need to know B contains here. So to prove this, we shall just need. So this is or we just need. We just need this zeta x is contained in B, because this is generated by what is zeta x. So you just need this d to the x is contained in B. But what is a n zeta x? This is by definition. D to the x is just this. So a n dx is just z minus 1 to the power n. So it's just, so this always goes to 0 as n goes to infinity. So thus you can prove this B is nothing but C0 ZPL. So that's what's left. Be short. Now we can have, so we give some new notation. So for any I is contained in N, we let L of I is either 0 if I is 0, or log I over log P plus 1 if I is bigger than 0. So what is this? This is the least integer n such that p to the n is bigger than I. Okay, so it's the smallest integer So this smallest integer such that p to the a is bigger than I. We just let Li is this. Now for any h is contained in n, we let LCH ZPL is functions which are locally constant, not all local, at every a plus p to the h zp. So this is a finite vector space, and so the proposition is this. I plus p to the Li zp. So 0 less than I less than ph minus 1. So that's not in my notes, this part. Okay, form a basis. It's a real basis of LCH. The second part is, so I is contained in N is a basis of LC. LC just means just locally constant. It's just all locally constant function. So this is also a real basis. It's not a Banach basis, because you cannot talk about completion. You take completion, you get C0. So now this one, is again is an orthonormal basis of C0, ZPL. So for Mayo's theorem, we get a basis is Xn. From this proposition, we get another basis. Now this is Banach basis, also normal basis.
Excuse me,
yes?
The definition of LC sub H.
Yes?
What is A?
So it's every A. So every coset.
What is A? Is a point?
Oh no, so you have ZP. Yes, you can get is like A plus PH ZP, right? Yes. So any A. Yes, you just divide about as a so you can say as a point. Yeah, it's just like this. So just say in that part is always constant. So it just means that this is a finite vector space. Is okay? Now, so I will explain this proof of this proposition. Probably is more clear. So basically, I think we just need to prove 1, because other thing is just corollary of 1. So let's see the proof of 1, and then we can see what is A. Okay. So proof of 1. So let's see, what is LCH ZPL? Basically has a basis 1 I plus PH ZP 0, right? So now this is a L vector space, so it has a basis like this. So if you really want to say, okay, which are for every, you can say 8, every coset of ZP modulo PHZP. Yeah. So that's this basis. Now you can see the number of these is equal to the number of these, right? So now we just check 1I plus P to the Li ZP. Note that this is nothing but it's just J is 0 to the P to the H minus Li, and this is minus 1. And 1I plus J P to the Li plus P to the H ZP. Okay? So first we have the number of these two are the same, and then this identity means if you write all this 1, 0 plus PL0 ZP, 1 plus PL1 ZP, 1 P to the H minus 1 plus P to the L P to the H minus 1, but this is just H. ZP. You can get this is a matrix. I think diagonally are all 1, and this is 0, and this is, you don't have to care about it. But here is 1, 0 plus P to the H ZP, 1 plus P to the H ZP, P to the H minus 1. It's just this. Because this is an invertible matrix, so certainly, if this is a basis, this must also be a basis. Okay? So this is a proof of 1. You just need to take a look. So converse. So now we have two bases of the C0 GP. ZPL, you have F. So F you can ANF, XN. You can also have BI F 1 I plus P to the Li ZP. Okay. Since this you can say is smaller coefficients, and since this is a Mahler theorem, so this is he called is Mahler basis. And this one he get a very bizarre name, but I cannot find it, the English translation, but maybe it's just wave basis. And the coefficient, he called this coefficient amplitude. Okay, so this is from physics, the amplitude. So we have two bases, also normal bases. Okay. So we finished this section. Now we talk about locally. So we just here is locally constant. Now we need to talk what is locally analytic. Locally analytic function. Okay, so here we first give some definition. So for any A is containing L, I is containing R, we get this B AR, probably different from my note. It's about the same thing. So it's x in CP, x minus A is bigger than or equal to R. So it's just say in the picture you have A and then you have something like this. Okay?
What was R?
R is any real number. Okay, any real number, yes. So it's just a ball. It's just a ball, okay? So B just means a ball. So now a function with f b AR goes to CP is called L analytic. What is L analytic if? So if we have AK, so basically it just means in this ball f can be written as a power series centered at A and with coefficients in L. Okay? So if we write down this, it's if this exists for any k, and the f of x is a power series. So usually analytic is just a power series. Okay? So AK f of A x minus A to the power k. You need this to be convergence. So to convert it, so you need this VP of A k f of A plus KR. So for example, if you choose x in the boundary, so you want this term goes to 0. So this term goes to 0. So goes to infinity is k goes to infinity. Okay? So this is called L analytic. So if you want to talk about analytic, you first talk about in this ball, and then we can merge them together, we get a big picture. So we get this VB AR, we just write down like this. Because this goes to infinity, you can take about this. Plus KR. So this is a valuation of f. Now we can find. So let A, B, A, R, L. So this is a set of L analytic function. In BAR. Then we have the first thing we have this A is Banach. And under this semi-valuation, you can see this is Banach. And actually this is more. And the other, we have, you can find this basis, because you can always find write this as this. So you can have this basis is x minus A to the power k over p to the, you choose Gauss integer of kr. So you choose the Gauss integer of kr. And then for any k contained in N, you can check this is contained in there, is a Banach basis. And moreover, if R is contained in Z, this basis is also normal. So this is so locally you just choose what is the function in this BAR. So this is easy to find because you can always write on it like power series. So you can make the polynomials or even monomials as a basis. Now we can find a proposition. The first proposition is if F1, F2 are both contained in this B, A, R, L, then the product is also there. So that means this is not only a module or vector space. You can have product structure there. Could be an algebra or a ring there. And if you take this VB AR F1 times F2, you can check F1 plus F2. So we are now increasing a lot of notations now. So you have this. This is, I think this is easy. So you just think about this. If you have like ANXN, BNXN, F, G, you can forget about it. Some FA minus N or something like this. So F times G, you know, Cn, Xn. The Cn is I, AI, Bn minus I, right? Now you just need to use a p-adic, is a very easy p-adic exercise. You just check the valuation of Vp, Xcn. So what does this mean? So this just means if it just means VPCN, VPAN, VPBN. So this is this is just this proposition. If you really translate to this, okay? But this one in real number is not true, but in complex analysis, this is probably not true. But in this p-adic analysis, this is always true. You can even find an easy proof about this, okay? Or you can. So this is this proposition. And the another proposition is if you check this VBAR F, you don't want to always have the Taylor expansion of f of x, right? So you want a little bit better. So you just take all these. So x, Vp, f, x. So you just take all this and find the smallest number, and then you can get this. Okay. Both of these you can find in the notes, but maybe in a little bit slightly different language. Now with this we can define another notation now. Now if H contained in N, now when you define this called LAH ZPL. So L means locally, A means analytic. Locally analytic, H means a level of level H, ZPL. So what is this? This looks ugly, but it's easy to write. So first, certainly you use a function from ZP to L, and F, the restriction of A plus PHZP. So A is for any A. The restriction of this, so this is function inside here, is a function FAH restriction A plus PHZP. Yeah. Well, if AH is L analytic on BAH, okay, so you should know this BAH, so this is ball, is in CP, so it's much bigger than this. So but what this means, like this looks like a pieces or gluing together or this analytic function, but you only define this analytic function over ZP. For this FAH, you always define is over the ball. So the domain is much bigger. Okay, so it's just all this kind of function. So this is for any A, You get this? But suddenly, because you don't need to for any A, right? You just pick a set of representatives. So like pick S, a set of representatives of ZP modulo P to the H ZP. And then the definition, so here is for any A, so you can change it. And you can change for any A to for any A contained in S. So that's it, right? Then not is finite. So this is because this is finite. Otherwise, it looks like you verify infinity times. So this is LAH. This is if you want to find this locally analytic function of, you can say, level H. So you may ask, why do I need all this level? Because if you just say take H is 0, and the space is very small. Okay, so now we need this valuation. What is this valuation? The valuation is just all this A contained in ZP, but or you can replace A contained in S. Okay, now and then VBAH. Now it's FAH. FAH is this. Okay. So this is the valuation. Under this valuation, then LAH ZPL is a Banach space. Then, okay, because you can check because all this A, B, Z, B, A, H, L are Banach, and then it's easy. The other things, we can write this LAH a little bit slightly better. If you see, VBAH, F of AH, what is this? This is K contained in N. So if VP AKF of A, so this is if. This is by definition. Okay, sorry. So this is a boundary space. We can write a bit more. So if we can write, if F in the, if Fx, you can write down as this, right? K 0 to infinity, AK F of A, x minus a to the power k over p to the h, because this is the basis in near a plus p to the h Zp in this, because by the definition, F you can write down as this, but this one in this BAH can be write down as this, But now you take a restriction, so it just means Fx you can write down like this, right? So now you can get LAHF. What is this? So if you first, if you get is A contained in S, BAH, FAH. But this one is nothing but in the middle one, K contained in N, and VP AK FA, because we already divided P to the H, so you don't need to plus times HK, so you can write it like this, okay? So if you take these two infinity together, you just take this, okay? So this is the valuation. Sorry. Now that this valuation, we can have some basis for this f of x, because you can locally, in here you can write down as this. So the first one is if we, for n contained in n, so this is amazing, it's a lot of n to the ph minus I, and 1 less than I less than to the pH. Then we let E and H is I plus P to the H Zp of x. So you just say A, and then you have x plus I over P to the H, and then M minus 1. So this M is related to this H, so you get this H. So the first is lemma is this, and is a also normal basis of LAH. So you can even say it's QP, because this function is defined over QP. So this is also normal basis. So and a corollary is you can have GPL, because we have an also normal basis. You can always take a tensor product. It's just the same. This is just the same. Okay. Anyway, there are many notations, but the C is the main point here is you want the existence of orthonormal basis. And also there's another theorem, and this theorem is even harder. It's like this. If this one, n over p to the h, so we take the Gauss integer and then take factorial and choose xn, n contained in n, then form an orthonormal basis. H, you can dp or dp to the L or dp to the Q. So this one is still, if you are more patient, you just take a look at this. You can find this is really the case. But this one, they need some proof. And I cannot prove this here, but I write down in my note. Okay. The thing is this. The ideal proof to prove it. So if we say this is Gn, or you say GnH is Gn, okay. What are you if you want to prove is an orthonormal basis, if you want to say a boundary space, then this basis, you need always this, the valuation of this is 0. Okay, so first, you need to show this V LAH, this Gn is always 0. Just means this Gn is contained in LAH 0. Okay, and how do you prove this? Then you have to relate this Gn to this ENH, and then to compute it. This is the first step. The second, you already proved this is 0, and then you need to use. Then we need to prove it. Then you need this Gn, and contained in n. Generates LAH 0 over P LAH, LAH 0 dP QP over LA P times LAH 0 dP QP is FP vector space. So this is when we talk about the boundary basis. So if you want to say something is really an orthonormal basis, you just need to check. First, you check the valuation is 0, and then secondly, you check this generates as a vector space. But we already know this ENH is an orthonormal basis. So this is equivalent to check this Gn bar, just means modulo P, can be written related to this ENH bar by an invertible matrix. Of course, this looks like an infinite inverted matrix, but if you can express each other, and then they are the basis. Okay, so this is the idea to prove. So 2 steps, the first step and second step, but these 2 steps are not so easy. But anyway, because of this theorem is a theorem of Amis. So that should be in the 70s. Because of this theorem, we have at least we have a corollary. The corollary is you have this V L A mu F. What is this? If you can write if write down is N, because if it is already, if we can write down like this, and then what is this? This one is just N is contained in N, and ANF times what? Times this. Factorial to the -1. Sorry. Just the valuation of this, right? Because that's the definition. And now you can look at this definition. If this one, VP of this, that's the, so this is VP ANF minus VP okay? So it's just this. So this is one of the corollary we need. And now if n goes to infinity, you can find this. This is what? This is about, you can check it. Yeah, 1 over p minus 1 to the pH is about this. So just means if you want the F, so F is contained in LA mu, no, this way, H, sorry, LH, ZPL, if and only if, then for n goes to infinity, this one must go to infinity. So this one minus something must go to infinity. Okay? We need to use this very soon. So I write them here. So this is just the level. In the level, we have this H. Now we have the total analytic function. It's just an inclusion of all, the union of all of these. You can see this is a direct limit, okay? So, but you have to, so we see, this is a Banach space. For every H, this is a Banach space. But this is a direct limit. You can, H goes to infinity. So this is not a Banach space. So first thing is, LA ZPL is not Banach. But because it's a direct limit of Banach spaces. Okay. So we take the topology. We can give some topology to here. So the topology is induced by all the topology in here. So it's a Fisher space. Okay, it's a Fisher space, and you resolve this. And so we need to know what is the functions there. So what we can say is phi, if LA goes to B, it's continuous. What this means is, this just means phi LAH goes to B, continuous for all H. So we also have what is F N. So if what is AN goes to A, or FN goes to A. So that means there exists H such that FN AN is contained in LAH, and AN for all N goes to A. So this is what is the definition of this Fisher space? What is a continuous function? It just means the restriction is continuous. The convergence is just the convergence in some level. Okay, so because this is include to each other, so we can talk about this. So this is LA. Now because of this condition, because of the theorem on this condition, so now you have a very important corollary about this LAZPL corollary. So if I write down as a Mahler coefficients, so first F is continuous, otherwise you cannot write down like this. Then F is contained in LA ZP or L, if only if what? If only if this goes to 0 to plus infinity for some H, right? It's contained in H. So for some H. But this, when H goes to, H is bigger enough, then this is just some positive integer. So this is if only if Vp ANF minus Rn goes to plus infinity, force, you just need 1 R bigger than 0. For any R bigger than, for some R bigger than 0. So that's how do you find a function is really a locally analytic function. Okay. You see here, right? Because of this.
You need to multiply by F.
Yes. So you mean F contained in this LA. So just means F is contained in some LAH. So just means there exists something. So this goes to plus infinity.
There over there, you don't have N, but there on the right hand side.
Oh yeah. Okay, so this one, I think. This is 1ON, right? Yeah. So this is 1ON. So this is 6. Or you can even, if you want to write in a more fancy way, it's just this. Lim, imp. Anybody still remember what is lim if? Okay. So this is just a notation. Lim if or this is bigger than 0. Okay. So I think today I will just stop here. So basically, what we learned today is just say this space and this space. I think this is the most two important thing. And say if you have a y, you can write it like this. Okay. So tomorrow I will talk about the dual of this. So the dual of this will be measures and distributions. And now then you'll be much more interested than this functional analysis. Okay. So I just stop here.
Any question? Okay, we'll do tomorrow at 3.
Okay. Thank you.